All right. So, as Mikhail said, my name is Hamza Tahir. I'm one of the co-creators of ZenML, which is an open source mlops framework to create reproducible machine learning pipelines. We are based in Munich, Germany. We're also a startup, but currently all of our code base is open source. We just started quite recently, so like relatively new to the game. I myself, I'm a machine learning engineer. I guess nowadays that's what I would be called if I was working in the field actively. I worked with a lot of startups here in Munich, especially putting some models into production at scale, seeing how things break and seeing how things work, which led me to found my own startup where we struggled with similar things, and then we eventually pivoted to what is now ZenML and the new efforts towards contributing to the mlops community. So that's on my side. Today I'm going to be talking about, or trying to convince everyone in the audience why they should start writing machine learning pipelines from training day zero. I find it's one of the best ways to eliminate technical debt. I will not be talking about my framework or our framework, ZenML, a lot, except as an example. Towards the end, I will also show a demo. But bear in mind, it's not about that. It's more about the ideas and to get your feedback. It's the first time I really talk about these things in this particular way. So I'm very happy to share these new ideas today in this conference. All right, then let me get into it. So we have to start from the top. So machine learning really powers 1% of today's most valuable organization. This is obviously, don't quote me on this. There's no McKinsey or Deloitte source to back this up. This is purely my intuition. I feel like a lot of people in the audience might agree, actually. Well, if it's 1% or 10%, it's a minority. For the rest of the organizations or the enterprises out there, it's very hard to implement machine learning still, especially when people change, when the data changes, when the organizations change, the code and the models. There are so many things in machine learning which are different as compared to conventional software engineering 1.0, which really brings to the front the importance of the ML toolings or the MLOps toolings that are coming into the fore nowadays, because you need that. It's not really a simple problem. And I'm not saying that the conventional software engineering was a simple problem to begin with, but on top of that, you have the added complexity of data. And that just completely makes everything that we talk about today even more complex, not even, I would say exponentially so. So it's not just a doubling factor. But that's why we have our conference anyway. Let's go one step deeper into this whole process. So if you look at the machine learning lifecycle, so this is my representation. It's a bit simplistic in its, like by all means, of course, there's some companies that do it smaller or just have one step, some companies that have multiple steps. But what I've seen is that the machine learning lifecycle, how machine learning develops in an enterprise or even a small company, starts with these three phases, or starts and ends with these three phases. The first is experimenting and proof of concepts. The next is a conversion step where you are actually converting these things into pipelines. And the third is the productionization and maintenance of these pipelines. And there's a plethora of tools that people use to get there. So let's talk about each of these phases in turn and what I mean by them. The first, the most obvious one, experimenting and POCs. So there's a lot of technologies that are used here, but I'm going to say the one that comes to mind first is a simple Jupyter notebook. It's still surprising how, well, maybe it's not surprising, it's just a great tool, but you see that a lot of enterprises start exactly from this point. You have one or two people sitting, looking at some CSV files in a Jupyter notebook. And that's fine. There's a lot of people who does that, but that's how basically everyone starts. And the goal of this phase is you want to have a quick and scientific experimentation. You want to get as much value out of your data as possible. And you want it to be fast. You don't want it to be super, let's say, proper or too much overhead on top. And the people who are doing this are basically data scientists. Next, the conversion phase. So we have these ETL pipelining tools, especially in slightly bigger corporations, let's say scale up onwards, which have data pipelining anyway outside of the machine learning team. And then these data engineers, they try to convert the machine learning code that has been produced in the experimentation phase, and they put it into stuff like Airflow or Kubeflow or any other tool. So converting these experiments into automated, repeatable processes is the goal of this phase, because that's how production works, right? It's not just about having scripts in like dev laptops not really tracked anywhere. It's a lot about having full control and idempotency and all these things that are very important for production. And then there's another step which I put slightly separate from the conversion, because it can be part of it, but it can be before it, after it, but it's essentially that it's about the productionization and the maintenance of these models. So if you get a model artifact out of your experimentation phase, your ML engineers, they come in and because they know the ML tools that are used for productionization, stuff like Cortex or Selden, they actually take these, they deploy them, and it can be part of a pipeline, cannot be. Sometimes there's disconnect. And the focus is really starting from the deployment to retraining, maintenance. You can have stuff like Arise AI or some monitoring tool, or Evidently, as we're going to hear in this conference. And then you essentially have like another pipeline step which retrains and pushes it using TensorFlow serving or something. There's many ways to do that, but the skill set involved here is also quite different. And this is where ML engineers come into the play. So if you look at all these phases, you see a problem. Well, you see a pattern first, and then you see a problem. So the problem is you have these experimenting to productionization. You have different people with different code bases, with different tools that start with the model, create it, and then the model goes through a series of destruction and construction until it ends up in production. And there are these gaps that exist between these phases. And within these gaps lives technical debt. And that's essentially how most enterprises out there are suffering, as far as I've seen, that they cannot really manage this technical debt. It's very hard for them because it's such an, as I said, things change. So organizations change, people leave, the data changes, the code changes, the models change. There's so many things that change. And there's no real layer that unifies everything, or there's nothing yet, but we're trying to come to it. But I feel like there's a big problem here currently in the landscape. Okay, so that was the orbital view, right? So let's go into the details. The data scientist produces code like this, right? And this is not to be disparaging, but this is also how I did it, to be honest. You have notebooks, you have cells, you execute, and you fit stuff, and it's NumPy arrays and pandas and all that. And the problem is you can't really take that and give it to an ops engineer and say, please productionize it in Airflow pipelines or something, right? So when you give code like this to ops people, this is how they react, just like SpongeBob when he can't find his name. So if you flip that paradigm, if you ask DevOps, if you ask the data scientist to actually write production-ready code or ETL pipelining, or even the modern ML pipelining tool, it's very hard for them because they are not used to code like this. They are not used to clusters. They're not used to bash scripts or Docker images or stringing together different microservices. And it's just something that they're not trained on. They might be a PhD in physics. They can learn these things, of course. It takes some time, but I mean, then they eventually become more engineering driven, excuse me. But not everyone wants to do that, right? I mean, if you're developing really complicated self-driving car algorithms, you want to focus on that. So that's how some data scientists, I would say most data scientists, to be honest, feel when they're shown code like this. So this is the problem. So we have a disconnect here, right? We have on one side the need of a data scientist to want to iterate or to want to rapidly produce results with the tooling that they're familiar with. And on the other hand, we have the need of the organization, of the ops people, to has a checklist of things that they need to fulfill, whether there's a legacy code base or whether there's systems in place to keep everything in check. They want to have both of those. So What is the solution? So I feel like the solution here is better abstractions. So, and that's really the crux of my talk today. So when you hear the word abstractions, I know it means a lot of things for a lot of people, but for me, I've been inspired by abstractions throughout my software engineering journey. For a lot of people, for example, would have been mightily relieved when Francois Chollet came up with Keras, and they didn't need to write the TensorFlow code of 1,000 lines, because you could just do model.fit and model.add. So not only did Francois come up with Keras, he came up with an abstraction which made TensorFlow accessible to pretty much a wide variety of audiences. And now we have an influx of data scientists who know it very well. They might not know the real details of it, or a few of them might, but they know the abstraction, and that is enough. And if you look at that, if you really take a step back and you look at abstractions in a more orbital or in a global perspective, you see that better abstractions across software engineering have a lot of huge benefits. You increase ownership of the code base if you have better abstractions. You have faster iterations, you have better coordination, easier testing, fast debugging, coordination is easier, mindshare is easier. It's if you have a layer of communication or a layer in your whole software engineering stack that can actually talk or speaks the language that these different stakeholders and personas have. And that's where I feel like we can take a look at web development. Web development, I mean, I was a web developer as well at one point, and I was very used, so I came from the HTML, JS, jQuery world, right? So these things like React, if someone is familiar with it, were not really common. So what happened was you ended up writing code like this. So it's like 1,000 lines of JavaScript code. This is just to produce a simple star widget on an e-commerce website. And you had to maintain state, like you have to write if reverse, if is touch, you have to do this, that, you have to manage so many things on your own, all the variables. And it was hell, honestly. It's one of the main reasons I wasn't a web developer. I should have waited a few years because Facebook came up with React. I'm not saying it's super easy now, but at least it looks cleaner, right? And if you look on the right-hand side, you see that the HTML is nicely embedded in the forms of components, which is the main first-class citizen of React. You can abstract away a lot of the complexity, and you can share these components. The state is managed on its own with things that a web developer could understand, stuff like on change, which is a JavaScript paradigm that everyone understands. It's baked into that framework, and it's very beautiful. So you can boil down 1,000 lines of code to very little, leading to less coordination, less friction, less debugging, no duplications, and so on and so forth. And if you go back to that picture that I painted, I feel like this is what's missing, and this is something that we need to work on as a community. We need a higher order abstraction that fills the gaps between the different personas in a machine learning enterprise. And we need to increase ownership of the data scientists to their pipelines and eventually their models. We need machine learning pipelines which are production ready from day zero. The talk, of course, is encouraging you to do that, but I haven't really given you an answer on how to do it. But by this point of the presentation, I hope that everyone is motivated to do it in order to avoid this technical debt problem in the first place. Regarding how to do it, I'll get to that in a bit. If you look at the whole tooling landscape that I showed you, there's a lot of ML tools for ML people, a lot of ops tools for ops people. I feel like there's not a lot of stuff in the middle. So something like an ops tool for an ML people or an ML person that is understandable and graspable. And this is where I have to segue into ZenML. I mean, it's the only example I know which is tackling this in this way. Of course, disclaimer, I'm one of the core maintainers creating it, but of course, you can use some of the ideas here or all of them and build on top of any tool that you see in the great space that we're building together. So ZenML looks a bit like this. Again, I'm going to compare something like Kubeflow on the left. Qflow is a great tool, but it's very complicated. So I used it a lot since its inception. And if you go from the top, there's a direct comparison to ZenML code, which is on the right. So first of all, you see it's another 100, 200 lines of code. You have like a GCS bucket, which is pointing randomly somewhere. It's not really being tracked. Like, for example, you saw in the DVC version, things were being tracked. But here it's not really, or not in a way that's accessible. Then you have the exit handler. You need to understand the DSL. You need to understand exit handlers. You also need to understand what cluster operations are, and essentially understand what clusters are then, right? That's more ops-centric. You have these bash scripts and these image versions, which I have no idea about, right? As a data scientist, I need to learn Docker and all that. You have arbitrary non-standardized steps, meaning you can string together as granular or as non-granular a step as you want, which is, of course, it gives you full flexibility, but it doesn't really tell you how to do it within the framework. So things that I loved about React or Ruby on Rails in the web development framework was that it hinted towards best practices. It allowed you to do stuff flexibly, but it also gave you that golden path. Then you have this unpredictable, untracked configuration. So you can specify project, region, and all that. Of course, unlimited configuration means very hard to track again. You have random data formats flowing between these steps. You don't really know how it's stored and what the schema is and how the schema is changing. And finally, again, coming back to that Kubernetes secrets and DevOps knowledge, if you see this piece of code, you need to know what a secret is. You need to know how to transfer that into a pod or something which is running on Kubernetes. These things are very hard, right? I mean, it's someone who's really specialized in both worlds would probably understand how to string it together, but not really a normal data scientist. On the right-hand side, you see it's a lot less code. And this is where ZenML is coming in. I go to the next slide, it's a bit more blown up, so you see how it looks like. So here you have, as compared to the last example, you have pipelines as first-class citizens, meaning that they're first-order classes or objects within the code itself, and you can treat them and manipulate them directly. Data is treated way more stringently. So you have data sources, a concept of data sources, which is important. So because you need to track all that stuff, right? If it's a CSV file or if it's a database, you need to know at what point the experiment started or the pipeline triggered, and you need to know exactly the snapshot of that. You need to have integrations, so you can't really be locked in. I mean, I know there's the cloud offerings that are available, like SageMaker, they have this problem that it's very hard to integrate with other toolings. So for example, here we're integrating with Hugging Face natively, and there's other examples for maximum flexibility, which I feel like is the most important part of the puzzle for the data scientist. Then you have familiar language as these. So the APIs that we are exposing at ZenML is really native language to a data scientist. So something like a random split or a trainer or a deployer even, it's really understandable because that's what they do in the Jupyter notebooks anyway. And the interfaces, if you go into more detail in the docs, you'll see that the way you just need to override some functions and put stuff where it belongs in order to really take advantage of ZenML very fast. Which is another way of giving higher order abstraction, which is easier to consume and therefore proliferating better across data scientists in a team. Eventually, what it happens is that it increases ownership of deployments. I mean, that's exactly the goal. If you have the data scientist who owns it till deployment and retraining, it's just going to be better for the ops people to support them and sort of plug in the backends as they go along, and they can just use it at the front end. So that's more of a better role than having a complete cutoff and a reduplication of the entire code base, which is more common nowadays. Finally, iterating locally and scaling on the cloud, very important. If it doesn't work locally, I don't think it will be adopted. So there are many tools, cool tools that work locally, but some just work on the cloud or just some work locally. I think you have to have both. So with ZenML, we're trying to tackle that. Cool. I'll give it 10 seconds so that people can read it because I know this slide causes a bit of sometimes confusion, sometimes at least interest, whether it be faint. Awesome. So let's go to a demo, shall we? Right. So I only have a few minutes. I'll go through it quickly. This is ZenML, so you have to do ZenML init and all that on the command line. It's also command line native as well. So we really believe in that as well, that it needs to speak all those languages. And then what you do is essentially, if I don't have any technical difficulties, live demos. So yeah, so I'll show you here is an example of creating a pipeline, which is an experiment. And you can then create another pipeline, create just a feed for your network to do the experimentation. Can you guys still hear me? I got a message that the connection was poor.
Yes, we can hear. Yeah, it was a bad connection, but for a few seconds. So, but we can hear you. In general, it's okay.
Amazing. My apologies. All right. So what I'll do is I'll create a training pipeline, again, a first-class citizen. The pipeline is created. Then I'll create my data source. This is just the Pima Indians diabetes data set. It's a binary classification, simple sort of toy data set. It's a bit like the code is not so important. It's just, I think this line is important. You point it to a path. This time the path is going to be tracked centrally, and you're going to be able to, for example, get the data source by name. If you want to, it will be having a unique ID and a unique hash associated to it. Then the fun part. So you have a random split. So these are all sort of internal splits, internal steps within the pipeline. So you have, just like Scikit, you have a lot of pre-built things like random split or like categorical split and all that. But if you want to create your own splits or your own steps, of course, you can do that. There's more documentation on that. You just need to override a class and create it, just like you would in any framework. I'm going to do a three-way split here. And then I'm going to add my preprocessor. In my preprocessor, it's using TensorFlow transform in this case. So it's gonna, if you want to, you can also distribute on Spark or on any Beam compatible backend like Dataflow or Flink. So this is pretty cool for scalability. But all you really need to do is you need to specify your features, your labels, and some other stuff, which is not so important for the demo. And then finally, you have a feed-forward trainer. You can see all the code in the examples directory of the repo. But what's important is that you have these parameters, and I've specified 5 epochs for this. I'm also going to add my evaluator step, so that's going to be after training, you evaluate on the test set or the eval set, and then I'm going to run, right? So the run is probably the most important of the commands, because you can run not only, let's say, locally, which this is running locally. It's a bit slow right now. My computer is bugging out. But you can also run on different backends, right? So just to show you the code, I won't show you this in practice, but you can specify, for example, a GCP orchestrator. So that's something that launches a VM on GCP. It can be a huge VM. It can be preemptible, so you save costs. And then after it's done, it's going to close it down. So you can also orchestrate on Kubeflow. You can orchestrate on potentially Airflow. So these are things that like ZenML has abstracted away from you. So you don't need to write in that tool's language. You can compile into it, which I feel is very powerful, because you just need to learn these higher order abstractions in order to really take the advantage of all these tools, right? And to have stuff which is production ready. Okay, so we're done. The final evaluator is done as well. Now we have a few commands that you can use to visualize your results. The first is one of my favorites, which is view statistics. This is using Google Facets again, something we borrowed also from the TFX ecosystem. but it works on PyTorch and all that. So it's pretty cool. You can see for each sort of split, you see your distributions. It's very cool because you can, of course, this can be huge data, right? So you can have a database on MySQL, run everything on GCP or something, or Kubeflow, but the results are still local to you. And you can just see your statistics. There's also this magic evaluate button, which actually creates 2 more cells within your notebook if you specify this argument. The first is TensorBoard. Wonderful, TensorBoard, come on. Okay, I'm going to do that in the background. It's the worst thing to run on a terminal. Suggesting. Give me a second, guys. I hope you can't see my bash terminal because I'm trying to kill the PID. Yeah, kill -9. Burn it. All right, come on. Don't let me down. Okay, so there's some port problem, but you should have been able to see TensorBoard right in your Jupyter notebook. And now you have, do you remember the evaluator step? In the evaluator step, you specified slicing metric. So you can actually slice your data across different groups and see the results not only fully, like you have this much accuracy, but also across slices. So this, for example, is my binary accuracy across people who have diabetes and who don't have it, who do not have diabetes. Cool. Moving quickly onwards, I know I'm running out of time. So you can actually get like a global instance of the repository that you're in. You can see that, for example, you have one data source now. It's versioned automatically. You can even sample it and put it as a data frame. So you can see the raw data, and you can see its columns because it's just a data frame. Now, here's where the cool part is. So you can create another experiment from the previous experiment and just change the trainer step. So the only thing I've done here is I've added another feed-forward trainer with 30 epochs, and now you can run it again. And the cool thing is it's going to skip straight to the training, just like using caching. And this can be with huge data. It's really beneficial because you have every step cached. And now it's going to be 30 epochs, so it's going to be this is going to run through it faster. Then we can evaluate it again and see the results. And hopefully it's going to be more accuracy. Cool. Let's give it a few seconds. We can already run this. Cool. So again, you have TensorBoard. I'm guessing it won't work again. Yeah. But then you have the slicing metrics again. But if you don't want to do that individually, all you can do is you can run compare training runs, which is actually going to open up another application locally that will allow you to compare all the different training pipeline runs within this, let's say, repository, ZenML repository. And that's something which we found is very helpful for a lot of people who just want a visual overview. Of course, this can get a lot better, and the framework is relatively maturing. So we have also an online dashboard, but this is something for just quick iterations. So it's usually not this slow, but my computer is really, I guess, can't really handle the stream. So I'm just gonna show you quickly. For example, if you select these 2 experiments, then you should be seeing that for each slice, so for slice 0 and slice 1, people who have diabetes, but people who don't, you can compare the different accuracies, and you can change between these. You also compare the hyperparameters. Let's see the epochs and maybe the batch size. I think the epochs are the min difference, yeah. So you see if you have more epochs, you're gonna have 80% accuracy, otherwise you're gonna have 70% with 5. So you can do a lot of stuff here. Anyway, so that's just a glimpse of the features. You can do a lot more, and we're still developing. We're looking for contributors as well. So let me go back to the final slide. So if you are someone who is interested in the ideas I presented today, then please go over to our GitHub, give us a star, or look at the issue board. You have some good issues to start with. Please also join our Slack. And there is a Towards Data Science article that I published to discuss more of these thoughts in further detail in this URL. So if the URL is not working, let me know. This is the full URL, why ML should be written as pipelines from the get-go. It's something I published 2 days ago as preparation for this talk. I can be found at hamza@zenml.io or on Twitter. And I'll be open to questions now. Thanks.